Today, we're tackling Lewis structures. You can think of them as the ultimate architectural blueprints for deciphering the hidden, microscopic world of molecules.
Okay, here's our roadmap for today. We're covering the molecular blueprint, the rule of 8, drawing your first structure, 3 molecular stories, beyond the basics, and why Lewis structures matter. Let's jump right in.
Section 1. The molecular blueprint. To kick things off, we really need to nail down what a Lewis structure actually is and why it's basically the bedrock of chemistry. Way back in 1916, a chemist named Gilbert N. Lewis came up with this brilliant, elegant concept. A Lewis structure is simply a diagram showing how electrons are arranged in a molecule. We use dots for the individual electrons and lines for shared covalent bonds. It's an incredibly straightforward picture that tells you exactly which atoms are connected, the strength of those bonds, and whether you've got any leftover electrons just hanging around, which we call lone pairs.
Now, here is a massive takeaway. Only valence electrons matter here. When we're drawing these out, we literally only care about that outermost shell of electrons. Why? Because the deeper inner electrons, they are completely ignored. They simply don't participate in chemical bonding at all. It's all about what's on the outside.
Moving to Section 2, the rule of 8. You know, what's really fascinating about molecules is that their behavior is mostly driven by a deep craving for stability, and chemists call this the octet rule. Think about it like this. Imagine each atom is a person at a super crowded party, and they desperately want exactly 8 people standing around them. To get to that magic number 8, they just share people, or in our case, electrons, with their neighbors. A shared pair counts for both neighbors. It's such a great way to visualize how atoms form covalent bonds to get that full outer shell, essentially mimicking the total Zen, unreactive stability of the noble gases.
But hey, every good rule has its party crashers, right? The rule of 8 is absolutely your best starting point, but you've got to watch out for a few exceptions. Take hydrogen. It only needs a duet. Just 2 electrons and it's perfectly happy. Then you have boron, which is perfectly stable, being electron deficient at just 6. And finally, heavier elements in period 3 and beyond can hold way more than 8 electrons using what we call expanded octets.
All right, Section 3, drawing your first structure. Let's open up the toolkit and see how we can turn this theory into a comforting, repeatable system for mapping out literally any molecule.
If you meticulously follow these 5 steps, you essentially have a foolproof cheat code. Step 1, count up all the valence electrons. Step 2, pick your central atom, usually the least electron-hungry one of the bunch. Step 3, connect everything with single bonds. Step 4, complete the outer atom's octets with lone pairs. And Step 5, satisfy that central atom. If it's short of 8, you just convert some of those outer lone pairs into double or triple bonds. Boom, structure complete.
Section 4. 3 molecular stories. Honestly, the absolute best way to grasp this process is to see it in action. So let's look at 3 classic molecules and uncover their very distinct personalities. Story 1 is water. Good old H2O. Following our rules, oxygen is central, forming 2 single bonds with 2 hydrogen atoms. That leaves 4 electrons left over, which sit right on the oxygen as 2 lone pairs. And here's where it gets cool. Those lone pairs sit on top like invisible ears and actively push the hydrogen bonds downward. This creates water's famous bent shape. That specific geometry makes the molecule polar, gives it a crazy high boiling point, and literally makes life on Earth possible.
Next up, carbon dioxide. Carbon sits right in the middle with its 4 valence electrons, flanked by 2 oxygens. But if we only use single bonds, carbon is not happy. It doesn't hit its octet. So the oxygens have to promote some of their lone pairs, creating some double bond drama. We end up with 2 double bonds and 0 lone pairs on the central carbon. The result is a beautifully symmetric straight line. And why does this matter? Well, those specific carbon-oxygen double bonds absorb infrared radiation. That is the literal mechanism driving global warming.
Our third story is ammonia, NH3. Nitrogen sits in the center, with 3 single bonds to hydrogen, leaving exactly 2 electrons to form 1 lone pair on the nitrogen. And let me tell you, ammonia has a massive chemical personality, entirely because of that single lone pair. It acts as a Lewis base, meaning it is super eager to just donate those electrons. Because of this, ammonia does the heavy lifting in everything from agricultural fertilizers to the amino acids building your own body.
Looking at these 3 side by side, it's pretty amazing, isn't it? Just shifting the number of bonds and lone pairs completely alters a molecule's reality. 2 lone pairs bend water to give us oceans. 0 lone pairs give us a linear greenhouse gas.
One lone pair gives us a highly reactive biological building block. It all comes back to the blueprint.
Moving to Section 5, beyond the basics. Because let's be real, sometimes these blueprints get a little complicated, and you might realize you can draw more than one valid structure for the exact same molecule.
So if you have multiple options, how do you pick the winner? We use a mathematical tiebreaker called a formal charge. It's a hypothetical charge we assign to each atom, pretending the shared electrons are split perfectly equally. The rule of thumb here is that your best structure has formal charges as close to zero as possible. And if you absolutely have to have a negative formal charge, it belongs on the most electronegative atom in the molecule, period.
But then you have molecules where one drawing just doesn't cut it. Take ozone, O3. You could draw a double bond on the left or on the right. But in reality, experimental data shows the bonds are completely identical. We call this resonance. There's a great analogy for this. Resonance structures are like the multiple outfits in a wardrobe. None of them perfectly represents the person wearing them, but together they give you the complete picture. The molecule is actually a continuous hybrid of those options.
Finally, Section 6, Why Lewis Structures Matter. Let's bring it all home and look at why mastering these dots and lines unlocks basically everything else in chemistry.
Look, this is way more than just a tedious drawing exercise for an exam. These blueprints dictate the physical interactions of our world. They're the foundation for molecular geometry, polarity, and intermolecular forces. They tell us where electrons are available for reactions. They explain acid-base behavior. They literally map out the organic chemistry mechanisms that dictate life itself. Once you master this, chemical behaviors stop feeling like random rules to memorize and start making total intuitive sense.
Which brings us to our final thought. Chemistry is, at its core, fundamentally about electrons. But how do the invisible desires of these tiny particles shape the tangible physical world around you? Whether it's the water you're drinking, the air filling your lungs, or the very DNA in your cells, it all comes down to connections. Once you figure out where the electrons are and where they want to go, the entire universe just starts to click into place.